Hello, thanks for coming to my talk entitled Is there any exponential algorithm that your operating system can run in almost no time? I will need to cover two subtopics, what you should answer a complexity theory professor, and secondly, what a practitioner may face in real-life computing. This may seem like a question a complexity theory professor may ask to decide if he has to fail a student or not. So, if you are a quote-unquote good student, to be sure not to fail any examination, always answer. This will never be possible on this planet, never ever. However, it may seem ironic, but if you also think this is the correct answer in real life, think again. I'll show you why it is more complex than that. Let me present the motto of my talk. So, it is given by the designer of C++. So, quote, if you think it's simple, then you have misunderstood the problem. Close quote. So, I took this motto because I think it applies perfectly well to the question I asked. More or less the same thing was said by a German philosopher some 1.5 centuries ago, but with much more insight and in a more easy to remember fashion. So, what is the misleading argument here? If you think that the answer to the question in the title should be something like "not, it's completely impossible, never ever, it's against the common sense of fundamental computer science," please remember the motto of this paper from the previous slide. By the way, both quotes essentially mean the same thing. Reality and practice can sometimes be so complex that they evade the belief system and the axiomatizations that theory has accustomed us with. I will present two programs that execute the same C++ instructions, as I needed them for a dynamical programming algorithm. So, let me introduce this C++ program. We have n equals 30. We have 2 power n using the bit shift operator. This is a real implementation detail. And here, these instructions allocate a memory area of size 2 power n plus 1, whatever plus 1 or not, but the memory is not initialized. So we have to initialize it here, then we perform some calculations, and in the end, the algorithm should output 7 times n. So let me compile and execute it, and take the running time. Okay, I started the program. It needed more or less 3.5 seconds. To show you this is an exponential algorithm given this memory allocation, I will replace 30 by 29, and the running time will roughly divide by 2. We have 1.77. This can go on even further. I take 38, and from 1.77 we have 0.88, more or less half of the previous running time. Now let me go back to 30, which took 3.5 seconds, and let me replace malloc followed by memory allocation. Let me replace this with calloc. If you check the documentation, calloc initializes the memory area, and it also fills it with 0. So it does the memory allocation by filling all cells with 0. And let me execute it. Notice the running time is virtually 0. So this is why I said in the title, an exponential algorithm that can run in almost no time. So This is an example that shows that the answer to the question in the title can, in real life, sometimes be yes, that's possible, at least up to the level of algorithmic insight offered by the C++ language. But how many people analyze algorithms by looking deeper than that up to the assembly language? Almost nobody. So what I want to say is that in real life practice of computer science, most people consider the two C++ programs I showed as simply different implementations of the same algorithm, and since we have any way to initialize a memory area of size 2 power n, this really looks like an exponential algorithm, and for most people, this is what it is, except that it may be executed in virtually no time. But again, pay attention. If you are a complexity professor, if you are a student and a complexity professor asks you this question, I advise you to answer no. An exponential algorithm is always exponential any way you implement it. Why confuse your professor with things he never considered or never imagined? If you ever need some service, a recommendation letter, he will prefer students who always only said things that agree to his knowledge. Because many professors and many teachers are only used to that. It's not systematic, but it may happen. And this is nothing new under the sun. I stumbled recently upon a quote from a man born in the 2nd century BC. He said, quote, "The authority of those who teach is often an obstacle to those who want to learn." So it may happen, and since human nature never changes even after 2000 years, I think it's better to tell the complexity professor, "Thank you for all the knowledge you taught me. It allowed me to implement very efficient algorithm, both in theory and in practice." But to continue, let me try to give some arguments, some clues to understand what happened, because we went, however, from 3.5 seconds to 1 milliseconds thanks to Kalok. The computational bottleneck comes from initializing this memory area of size 2 power n plus 1. We need to dive into this implementation detail, so-called code implementation detail, close quote, because it's not really a detail, to answer the theoretical question from the title. The program with Kalok has not really initialized the memory area associated with the array tab, around 4 gigabytes in 1 millisecond. There may be several possible explanations. The first one is that the operating system actually initialized the memory and filled it with 0 beforehand. Some operating systems use their idle time to fill all available memory with 0. Only just to be sure that the data of a terminated process cannot be accessed later by another process, so in some sense for security reasons. After investigating this possible explanation, I realized that this feature does not exist in my operating system, but it does exist in other operating systems. And this brings us to a question that I don't think theory alone will ever solve. What is the complexity of an algorithm if we know that a part of its code is anticipated by the operating system and executed before the algorithm starts? I really have no idea how to answer this question using only theory. Okay, let me go to a second possible explanation. The operating system might have performed a kind of lazy initialization. It is known that some processes offer asks for memory without using it right away. This way, the operating system might give just a form of pledge that it can provide initialized memory when needed. When the process really needs to use a memory cell, the processor triggers a page fault and the kernel steps in to allocate real RAM. Okay, I must confess that I could not execute my algorithm for n greater than or equal to 31. Why? Because my operating system does not want to commit to an impossible memory allocation. But a different memory management system may be coded to return a larger virtual memory block, virtual, for larger values of n, knowing this can be implemented in practice because if we know that the program will never use more than on cells. This gives this number of page faults to handle, so it's a linear number of page faults to handle, much different than an exponential one. The third possible explanation is that the compiler might have been very clever because I could not find the same speed if I replace J++ with JCC. G++ with GCC, sorry. The performance also degrades if we replace calloc with the C++ way of initializing memory using the new operator this way. It can everything can become more and more complex if we start using compiler optimization options. Like any truth, it is always possible to go deeper and deeper and find thousands layers. But this is outside the scope of this short talk. But I think it should be clear to everybody, or at least for me it's very clear, that I cannot answer in real life the question in the title by simply saying yes or no. It's more complex than that. This brings me to this conclusion. Let us take a higher standpoint and realize that many aspects of real life evade the understanding of those who do not go to the root of most questions because they only think on the basis of theory or only on the basis of summary information. This may happen even for some referees for journals, for journal acceptance, for PhD thesis committees and others. I have uploaded on YouTube here a demonstration of a program that can become 7 or 8 times faster if one has a simple call simplex.end at the end of a function. For those outside operations research, this simply signals to the program to finish with the use of an external library in the code. Usually this should take virtually no time. Usually this is what happens. This has no impact on the running time. But sometimes, for reasons very hard to detect related to the way the library is implemented, it may happen what I describe here. The program can become 8 times faster by adding this instruction. I stumbled upon this situation by practical experience. It only happened once, I must confess. But anyways, it can happen. And so the problem is that even if we assume that the world is only filled with very correct people, very honest people, it is easy to lie to yourself in such a case and to think that it is the theoretical contribution that has made your algorithm 8 times faster, when that may come from a simple simplex.end call forgotten by your collaborator. And let me, before finishing, let me say that this is a part of our larger work on similar topics, composed of several papers that I presented at the Operations Research French conference that is uploaded below. I invite you to go there. It's a kind of blog, if you want, but I really dislike the word blog, because when I hear the word blog, I think of superficial thinking. So it's not a classical blog. You have no connections to Facebook. You cannot like it, dislike it. It's only text. So let me say that if I decided to take the pain to write a dozen of pages, maybe even more in the future, I did not do it simply to reinforce well-known ideas using more original arguments. This is not the way I designed this. What I want to do is to challenge several preconceived ideas. I want to challenge all preconceived ideas I can find, ideas that have had a very negative effect or a very negative impact on computer science, usually because they disconnect too much theory from practice. So, thanks again for watching. Bye bye.